बंद करना गेट हुन्नू जी आवाज इंदा।
So good morning student, आवाज आ रही है? आवाज आ रही है कि नहीं? आवाज आ रही है तो write A and video is clear, then write V. A and V for audio and video. Okay, thank you. Write audio and video. Clear. So there were continuous session today. So in the last period, we saw the electric potential due to dipole. Here, electric potential due to dipole. That was Ohm's doubt, and he was absent yesterday. Ohm, yesterday you were absent, and that was your doubt in the previous period. So we saw we have a dipole. Suppose we have a dipole like this. Okay, and taking this side negative and this side positive. And here at any position P, okay, at a distance r from the midpoint of the dipole, we got the potential is equal to 1 upon 4 pi epsilon naught P cos theta divided by r square. This is the formula for electric potential due to what? Okay, electric potential due to a dipole, correct? And see, when we have two different positions, when the theta is equal to 0, if theta is equal to 0, V is equal to 1 upon 4 pi epsilon naught P cos 0 means it is an axial position, and the right side we have a left side. When there is negative side, this angle will be 180 degree. So if theta is equal to 180 degree, so that will get minus 1 upon 4 pi epsilon naught P, because cos 180 degree is minus 1. That we saw in the last period. And we also saw one more thing. When we have a theta is equal to 90 degree or 270 degree, that is a broadside on position, equatorial plane, ये वाला point. Okay, on these point here, you will get the V is equal to 0. So there is a no potential. Okay, there is a no potential. There is a no potential where in all these points the potential is 0. Clear? So these points are, just see here, the potential is 0. Here all these the potential is 0. But here we will find some of the potential. We just memorize, try to memorize when we are finding the electric field. Okay, जब हम electric field निकाल रहे हैं तब क्या था? This is axial position, and this is broadside on position. Just compare the given relation with the electric field. So in an axial position, we saw the electric field 1 upon 4 pi epsilon naught 2 P by R cube. Okay, and in a broadside on position, we saw the electric field 1 upon 4 pi epsilon naught P by R cube. This is okay, but the potential is 0. Okay, here axial position, and here broadside on equatorial भी बोलते हैं, equatorial plane. Here the potential is 1 upon 4 pi epsilon naught P by R square. Here the potential is 0. Correct? So just see two different things are there. What are that? Two different things. One, the sound is coming na today. Just see. Sound is okay na? So let's continue. So here, just see, this is the special point. This is the special point where electric field is present. Okay, electric field is present, but the electric potential is zero. It's very special point. So if anytime it is asked, okay, if it is asked that so if it is asked, describe any point where the intensity is not zero, but the electric potential is zero. So this is the point, friend. This is the point where the electric field is present, but the electric potential is zero. What is that? Broadside on position. The broadside on position of a dipole. There is electric field is present. Okay, but electric potential is zero. याद रहेगा? Clear है? So all of you write in the chat box. Where will it be? Okay, where will it be? The electric potential is zero, but electric field is present. All of you. Write in a chat box. Where will be the electric field be present, but there will be no potential. So there is a special point on an equatorial plane. There will be the potential. Clear? There will be zero potential, but there will be electric field. So just always remember this point. Now one more thing we will see. Just a reverse order means can you find any point their potential is present, but the electric field is zero? There is a electric potential, but the electric field is zero. Just a reverse of that. Here, what we saw, the electric potential is zero, but electric field is present. So do you know any point where the electric potential is there, but electric field is zero? Electric field is zero. Do you know any point where this thing happened? Means electric field is no idea. Anyone? See, actually, we haven't studied in a Gauss theorem application the electric field due to a sphere. Okay, electric field due to a charge sphere. If we have a metallic charge sphere, so there is no electric field inside the charge sphere. वो अभी इस साल सिलेबस से हट गया है फॉर दिस ईयर ओनली. तो आपको मैं हल्का सा आइडिया देता हूँ. मींस वी हैव ए स्फीयर. There is no electric field inside the sphere. Okay, but potential is present. What is the potential? That is V charged by R. This is the potential. Everywhere the potential will be same. Each and every point inside the charged sphere, metallic charged sphere. Inside the metallic charged sphere, there is a electric field is zero, but electric potential will be there. Okay, just a reverse order. Now, one more thing you will see, all of you, equipotential surface. Okay, so note down equipotential surface. Equipotential surface. What is it? New thing is this equipotential surface. Okay, equipotential surface. So, as the name implies that to see the definition will be very easy. The combination of all those points, okay, when you join all those points where the potentials are same, okay, the combination of all the points where the potentials are same, that is called equipotential surface. Is it clear, children? What is that? Combination of all those points where the potential is same. Okay, where the potential is same, that is called equipotential surface. Yes, that is called equipotential surface. Is it clear to all of you? Okay, equipotential surface. Clear? Now we will draw equipotential surface is a simple diagram. Okay, so when we show equipotential surface in our plane, so it will look like a lines. Suppose that we have a point charge, and you know near it at any distance r from here. Okay, you know the electric potential 1/4 pi epsilon q by r. Okay, so that is the point where the potential is this. When you see r is same here, r is same here, r is same here, r is same here. So all these points where the r is same, we have the same potential. So when you join these points, that we get an equipotential surface. Okay. This is a sphere. On these points, the potential will be same. When you take some other radius, say when the radius is changed, suppose here the r is 2 centimeter. Suppose the r is equal to 4 centimeter. So here also it will be same, but the two different equipotential surface. This is different surface. Okay. So here the equipotential surface, here another equipotential surface. You can make so many equipotential surfaces like this. Okay. So there are certain properties. Of equipotential surface. So just note down one by one. The first property, the equipotential surface is always perpendicular or normal. Normal to electric field lines. Okay, so when we have seen the electric field lines, so electric field lines you have observed, just try to memorize. When we have a point charge here, so this will be the electric field lines. ऐसा आ रहा है यार? these are the electric field lines due to a point charge, and these are the equipotential surface due to point charge. Just see, both are normal. This is normal to this. Yeah, this is normal to this, and that is normal to that. So electric potentials are same here, equipotential surface, and this is perpendicular. This is perpendicular to one another. Okay, each other. So this is perpendicular to this. Similarly, this is also perpendicular to this. So electric field lines and equipotential surface are always perpendicular to each other. Here, or you can say if there is a line, it will be normal. Here, next, two equipotential surfaces never intersect each other. Similar to electric field line. Two equipotential surfaces never intersect each other. And the third one, see, if the potential is same, equipotential surface means each and every point the potential is same. So if you are moving a charged particle in an equipotential surface, there will be no work here. Okay, so note down. There is no work is done. There is no work done. There is no work done to move a charged particle in an equipotential surface. There is no work done. If the work done is zero. Okay. So there is no work done to move a charged particle in an equipotential surface. Clear? So when we move an equipotential surface, there will be no work is done. No work is done. Yeah. So means the charged particle is moving here to here, here to here, here to here. It can circle a complete circulation. No work is done because so there is a each and every point the potential is same. Okay, each and every point the potential is same. So there will be no work is done. Here there will be no work is done. Clear? Now it is okay. Chaliye. One more very important concept we will see. Equipotential surface due to a dipole. Equipotential surface due to dipole. See, this is one of the very beautiful diagram. Okay. So, how to draw a equipotential surface? For that, there is a one trick. Okay, there is a one trick. You do one thing. You draw the electric field line first. You draw the electric field line and take a perpendicular points on that. So at a point, take a perpendicular dot line like that, and automatically you will get the equipotential surface. Okay, see how to draw this. Suppose we have a dipole. You know we have a dipole, and you know how to draw the electric field line to the dipoles. Electric field lines always comes from positive charge and move to the negative charge, plus to minus like this, 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 plus to infinity, infinity to minus, plus 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 to minus, minus. Like this. So these are the electric field lines. No, that you already know. Just see. You know, certain points where the potentials are same. Okay, say here. Here the potential is zero. You just know, see in an equatorial plane the potential is zero. Here the potential is zero. Here the potential is zero. Here the potential is zero. So all these points the potential is zero. Let's see, equipotential surface. This is the equipotential surface. And the potential is same. Now just observe, it is perpendicular or not. These two are perpendicular. Similarly, then draw the perpendicular line here. 1, 1, 1, 1, 1, 1, 1, 1 perpendicular. Just see. And Join them. Like this. Similarly, one more. Join them. Okay. So hence you will get the C here also. Join them. These red color lines, okay, these lines are equipotential surface. Similarly, you draw right hand side also here. Just symmetric to that. Take a symmetric to that. See, like this way. Like this. Like this. Okay, so this is the equipotential surface. So red color से मैंने draw किया है. That is equipotential surface. I hope it is clear to all of you. Okay, if it is clear, then write in a comment box. Yes, it is clear. Yes, it is clear. Clear or not? Write in the comment box, it is clear or not. So let's proceed further. Write in the comment box. Okay. So let's proceed. Now, okay, thank you. So let's proceed. तो ये एग्जाम में आता है इक्विपोटेंशियल सरफेस को ड्रॉ करने के लिए. आपको इट इज आपको यदि ये नहीं बनाना है, we have drawn two diagrams together. Okay, the red color is what? Red color is equipotential surface and the black color is electric field lines. Okay, and the red color is what? The red color is equipotential surface. So we have drawn together. So if it is asked to draw the equipotential surface in the examination, so it's not necessary. You can draw simply like that only. Okay, as it is given, you can draw like that. No problem. Okay, like this. So it is okay. But when you draw like this, if you suppose this question is already known. Suppose some different type of aspects is asked, and you know how to draw the electric field lines, because electric field lines, to draw the electric field lines is easy. Means you have to move the electric field, means you have to move your pen from plus to minus, and that will be easy. So first you draw electric field line, then you try to get equipotential surface by taking the perpendicular lines, so that you can get. If some other question is asked, ये तो आपको सिंपल है, समझ में आ जाएगा. ठीक है. Now, one of the most important concepts we will discuss now. That we in this electric field, capacitance, electric potential, everything is clear now to you. Now we will discuss energy of a conductor, energy of a charged conductor. Okay, energy of a charged conductor. Also, you can say capacitor, because the same derivation is there. Sometimes we use a conductor word, sometimes we use a capacitor word. So, if you are charging a capacitor, then also the same formula will come. If you charge a conductor, you know every conductor will have the capacity. Okay, so that will also you get the same formula. So when you are charging a conductor or when you are charging a capacitor, in both cases the formula you will get the same formula. Okay, so this we will derive today. Okay, so suppose we have a conductor and its initial charge is 0. There is no charge on the conductor, and when we are charging a conductor, so its potential will be raised. Okay, potential is increased, and if the potential is already increased, so it opposes the further charge. And what will happen? You need to put some extra potential to charge it further, and because of that process, some work is done. And whatever the work is done, that is stored in a form of energy, and that is called the energy of a charged capacitor. That is actually electropotential energy. Okay, just take an example. Suppose you are inflating a balloon. Suppose you are inflating a balloon. So you are blowing some air into the balloon. Okay, so what is happening? Just try to memorize yourself. जब आप एक बैलून को आप इन्फ्लेट करते हो, सपोज आप बैलून को फुलाते हो, अब कैसा होता है? So whenever you are inflating a balloon, so you have to maintain the pressure, okay, within the balloon. See what is happening. Suppose just imagine a very small child is inflating a balloon. जब आप सबसे पहली बार फुक्का फुलाया होगा तो क्या हुआ? Just try to memorize. First time, see what is happening. So you are inflating some air. Suppose you are blowing some air on the balloon, and all the air from the balloon is come out to your lungs again. ऐसे ही होता है. First time, just try to memorize. See, आपने फुक्का फुलाया और पूरी हवा वापस आ गई. फिर आपने फुलाया, फिर पूरी हवा वापस. That means what you have to do. So you have to blow air, and as well as you have to maintain pressure that the inflated balloon's air should not come out. Two things you have to maintain together. Okay, so you have to further increase the pressure continuously. You have to increase pressure to inflate a balloon. Are you understanding? Means initially the balloon was empty. There were no air within the balloon. Okay, initially there is no air within the balloon. So you blow some air within the balloon. Now there is some air inside the balloon. If you open it, what will happen? All the air will come out because the outside the pressure is less. So when you need to blow extra air within the balloon, you need some extra work. Getting or not? Same thing will happen here. So we have a conductor. Okay, we have a conductor. Very easy to take a spherical conductor. Its capacity is C. Okay, we have a conductor. Its capacity is C. Initially, its charge is 0. Initial charge is 0. Initial charge on a capacitor or a conductor is 0. Okay, initial charge is 0. And we are charging it to up to a final charge. Okay, there is a final charge. Okay? There is a final charge. क्या हो गया? So what is happening? There is a final charge. Say initial charge is 0, and the final charge, suppose it is capital Q. Okay. So in the meantime, in between this, suppose the at intermediate charge is suppose Q. Okay, at intermediate, suppose the charge is Q. So what is happening? The initial the charge was 0, then we are charging a capacitor, and as you charge the capacitor, its potential will increase, and if the potential increase, it opposes the further charge, and you need a further charge. To further charge, some extra potential difference is needed, and because of that, some work is done. Okay, and that work is stored in a form of electropotential energy within the conductor. Yes, so that we have to derive. So let us consider a conductor. His capacity is C. Okay. its capacity is C. Initial charge is 0 and the final charge is capital Q. Okay, final charge is, it is charged up to capital Q. Let Q be the charge at any time. Okay. So whenever we are charging at any time, it is let Q be the charge. Okay, and it is further increment of charge is suppose dq. Let dq be the increment in charge. What does it mean? Means it is charged q to q plus dq. Okay, initially absolutely beginning it is 0, but final is capital Q. In meantime, the charge is small q, and just we are taking small increment, and that delta q, that dq. Okay, so this is the small increment dq. So q to q plus dq. Yeah, q to q plus dq. That is the what? Q to q plus dq. That is the charge. Okay. When charge is q and it is increased to q plus dq, so there will be some work here. Okay. So when the charge is q at any time, so the capacity is C, the potential, it will be q by C. Okay, so as you know that we already studied in the definition in the very first period, when we are increasing charge, the potential also increase, but the ratio of charge to potential, that remains constant, and that is equal to C. So here potential is equal to Q by C. Okay, and what will be the work done on charging a small increment dq? Q to q plus dq. The work done. Say that is a small work done. It will be the charge into, it will be the potential into increase in charge. Okay. So the potential into increase in charge. That is the work done. Clear? So this is the work done, and the V is equal to here. But the V is equal to Q by C. Put this value here. Hence, we will get dW is equal to Q by C into dQ. So, this is the work done in terms of Q and C. Now, we have to integrate this. From initial charge 0 to final charge capital Q. Getting another? From initial charge 0 to final charge capital Q. क्या आ जाएगा? Okay. So total work done. To charge from 0 to Q. That will be integration 0 to Q. 0 to Q integration. So on integrating this, what shall we get? C, very simple. Integration of Q with respect to Q only. So it's very easy. What shall we get? So C, मैंने आपको पहले ही बताया था बायो वाले को इंटीग्रेशन में जाता है एक ही फार्मूला यूज होता है, and that formula is what? Basically यही वाला फार्मूला सबसे ज़्यादा यूज होता है on integration. Yeah. So we use this formula. Here the power is 1 plus 1. So W is equal to Q square by 2. And initial charge 0 to final charge capital Q. When you put this value here, so we get the final charge. Right. So this is the formula. Hence, half Q square by C. Okay, W is equal to half Q square by C. Clear? Now this formula is okay. Now this is the work done. This is the work done to charge a capacitor from initial charge 0 to final charge capital Q. Clear? Now this work is stored in a form of energy. This work is stored in a form of energy. So the energy we can write here. Hence, this work is stored in a form of energy. Correct? So the energy, ये एनर्जी है हाफ क्यू स्क्वायर बाई सी. ये फार्मूला आपको याद रखना है एनर्जी का. ये वन क्वेश्चन इज एवरी ईयर आस्क्ड as far as the energy is concerned. Every year one question is asked. Okay, now one more thing. Just see, you know one thing, if final charge is capital Q and capacity is C and the potential is V. Okay, final potential is V. Final potential is V, suppose, and the charge is already, you know, Q. So we can write that Q is equal to CV here. When you put this value, so energy will become, if you put instead of Q, CV, the C square, V square divided by C, what shall you get? Half CV square. One more relation. And also, when you put C is equal to Q by V, so you will get again half QV. So these three formulas you have to memorize. All belongs to energy. Clear? These all belongs to energy. Is it clear now? So I hope it is clear. So all of you just put your name and section. Just a minute. Just a minute. Your name and section. Let me record it. Okay. All of you put your name and section. Your name and here for attendance. Okay. Okay, so thank you. Thank you. Closing now.